What's going on, Linear Algebras? It's Mr. C here, and we're going to do a video lesson on some of the items in Section 4.7 note packet. In this section, we're actually going to investigate some fundamental spaces of just a plain old coefficient matrix A. So you'll see I have a particular 3x3 matrix A. Top row's entries 1, -1, 1, so on and so forth. And what I'd like to do is define some vectors that we could form using these entries, in particular using rows and columns from this 3x3 coefficient matrix A. The first vectors are the row vectors, and these guys are really easy to figure out. You just basically take each row and convert it into a vector, and I'm going to use the bracket notation versus comma delimited, if you don't mind. Row 1 can be converted to a vector, so could row 2, and so can row 3. So I'll write them out here. The row vectors for this matrix, we'll say R1 equals, and I'll just write it out as a row vector. So 1, -1, 1. The second row vector is formed by using row 2 of the matrix A. Let's write that. It's 9, 3, and 1. And then row 3 can be converted to a vector having entries 1, 1, and 1. In a similar way, we can define column vectors using the columns from the same matrix. In particular, column 1, having entries 1, 9, and 1, can be formed into a column vector. Let's write it down here. C sub 1 equals 1, 9, 1. The second column can be formed into a vector. Call that C sub 2. -1, 3, and 1. And then the third column can be converted to a vector. 1, 1, and 1. So why in the world are we doing something like this? Well, it's to form some special spaces. So a few definitions are in order, and then I'll show you some bougie notation for them. First definition, if A is an n by n matrix, so we're not just confined to square matrices here, then the subspace of Rn spanned by the row vectors of A is called the row space. The subspace of Rm spanned by the column vectors of A is called the column space of A. There's one more space that's fundamental to a matrix, and that is the null space. Basically, the null space is a solution space of the homogeneous system of equations, such as this one. So if we solve a system that is from Ax equals 0, then our solution vectors form what's called the null space. So there is some notation I want to introduce to you that's going to carry through over the next couple of sections. If we take the row vectors of any n by n matrix and we form all the possible linear combination of those row vectors, we get a span. And that span, or the set of all possible linear combinations, is called the row space of A, which the notation for it is ROW of A. It's kind of like function notation. If we take the set of all possible linear combinations of the column vectors of the matrix A, that gives us the span, aka the column space of the matrix A, which I'll write as COL of A. Now, as for the null space, that too is a span, but it's a span formed by all of the vectors x. Oops, that's not how I want to write it. Hang tight. Okay. Alright, so the span is found by taking the set of all linear combinations of the vectors, let's write them vector x, such that Ax equals the 0 vector. Alright, so if we can figure out the basis for this solution space, the set of all possible linear combinations of those basis vectors would give us the span, which in this section is referred to as the null space of the matrix A. Okay, that's it for this video. Nice short one there. In the next one, I'll go ahead and show you how to find a basis for the row space and the column space of a matrix A. So hang tight. I'll see you in the next one. Thank you.